In our gas laws podcast, we are going to take what we learned from our combined gas law and we're going to derive 3 different gas laws, Boyle's, Charles, and Gay-Lussac's, in order to look at the relationship between different variables that affect gases in an ideal situation. All right, so let's start with Boyle's law. So Boyle's law looks at the relationship between volume and pressure for an ideal gas. So the volume of your gas is going to change inversely with the pressure of the gas if your temperature is being held constant. So for this particular, and actually for all of these gas laws, we're going to start, and a beautiful graphic, using that mnemonic device that we came up with. So remember, our mnemonic device was, can this guy possibly be victorious? Always start on the right-hand side and fill clockwise. Let me just show you the magic of why we do this. So when we're talking about Boyle's gas law, we are talking about the volume and the pressure. We are holding the temperature constant. Okay, so with this that you are memorizing, I hope, you can just ignore what we hold constant. So we're holding temperature constant. So we are just for now going to pretend temperature doesn't exist. And what we're left with is pressure times volume. That is Boyle's, B for Boyle's law. All right, so that gives us our equation. And we know that we're going to have a change from an initial pressure and volume to a final pressure and volume. So let's look at this term inversely proportional, because that can be kind of a scary word. Looking at these two diagrams, your pressure is at 1 atmosphere and your volume is at 2 liters. So if we were to decrease the volume, so we've decreased it by half from 2 liters to 1 liter, your pressure is going to increase from 1 atmosphere to 2 atmospheres. So as your volume decreased, your pressure increased. So you're seeing an opposite effect with those two variables, and that's what we mean by inversely proportional. When we talk about Charles and Gay-Lussac's, you're going to see that those are directly proportional. It's a little bit different. This one's the only exception. So looking at our combined gas law, this is always a good place to start. If the triangle doesn't work for you, we can just think about what are we holding constant here? And we're holding temperature constant. So we're looking at the change between an initial pressure times an initial volume and a final pressure times a final volume. So Boyle's equation is this. P1 times V1 is equal to P2 times V2. We don't include temperature because temperature doesn't change. All right, so let's put this into practice. And this is going to seem kind of easy at first because I'm telling you it's Boyle's law, so you know exactly what equation to use. As you start to practice and you look at mixed problems, you'll want to start by identifying your variables because that will tell you which equation you're going to use. So let's read. A sample of hydrogen gas has a volume of 4.0 liters. I'm going to guess that's my initial volume. I can always change that. And a pressure of 1.0 atmospheres. That's my initial pressure. What is the new pressure? So I don't know what P2 is. That's a big mystery. If the volume is decreased to 2.0 liters. Okay, so let's go ahead and set up our problem. We can pretend I drew my triangle, but P1 times V1 is equal to P2 times V2. And my variable in question is P2. So I'm going to start by rearranging this problem before I get it all muffled, mumbled, jumbled up with my numbers and my units. So I'm going to divide by V2 because I don't want this to be next to P2 anymore. I want to move it to the other side so I can solve just for P2. If I divide on one side, I got to divide the other side by it. So rewriting this equation to make it look pretty, P1 times V1 over V2 is equal to P2. So now I'm ready to start plugging in some of those numbers. All right, P1 I've labeled as being 1.0 atmospheres times V1, which I've labeled as 4.0 liters. Okay, so I'm told the volume decreases, which means since these are inversely proportional, then my pressure should increase. So I would expect that my pressure should be higher than 1 atmosphere. And I'm just predicting right now what I think is going to happen. We'll see if it works out that way. I'm going to divide this by 2.0 liters. That is my new volume, or my final volume. Multiply across the top, divide by the bottom, and we wind up with 2.0 atmospheres for this. So my final volume has increased, which is what we expected when we decreased the volume. And I am going to maintain 2 significant figures here because there are 2 significant figures given in each of my problems. All right, so this next problem, which is a little tough to see, it is number 2 in your guided practice. I'd like you to do on your own, so you can go ahead and pause it. All right, so let's talk about Charles's law. When we're talking about Charles's law, temperature, which is always reported in Kelvin, we always use Kelvin for our calculations, is directly related to the volume of the gas. In this case, we're holding pressure constant. So looking back at our little magical triangle that helps us to remember everything, if we're holding pressure constant, I'd like you to think about this pressure being covered up. It's not involved. So what you have is volume, and a horizontal line means divided by temperature is Charles's law. So this is really helpful. If you memorize this, you've got everything else. And what we mean by directly related is if I were to start with a temperature of 200 and start with a volume of 1 liter, and I were to increase my temperature to 400, my volume is also going to increase. So they're directly proportional. So one goes up, the other goes up. Going back to our combined gas law, if the visual doesn't work for you, the combined is really nice. Again, we're holding pressure constant. So think about this combined. To derive Charles's law from the combined, you're going to remove pressure from it because pressure doesn't change. It doesn't need to be in there. It's not doing anyone any good. So when you hold pressure constant, the equation that you're left with is V1 over T1. Again, that's what we saw in this magic triangle. V divided by T is the equation. You just remember that your initial volume and temperature go together and your final volume and temperature go together. All right, again, this is really easy that we are told this is a Charles law, so we know exactly what equation that we're going to be applying. Keep in mind, the best way to find out is to label all your variables and see what you've been given to figure out which of your gas laws to apply. All right, so if a sample of gas occupies 6.8 liters, that is the initial volume, at 327 degrees Celsius, yuck, we're dealing with Celsius, we're going to have to convert that. What will its volume be? So I don't know what my final volume is. At 27 degrees Celsius, that is my final temperature. All right, so if we keep in mind the Charles law is V1 over T1 is equal to V2 over T2. We can solve this for our volume. So to do this, we're going to multiply by the reciprocal. So T2 over 1 is the reciprocal. We're not going to put anything in the bottom because we don't want to get rid of V2. So T2 divided by T2 cancels. And we're going to do the same thing for the other side. We're going to multiply it by T2 over 1. So let's rewrite this because it's a little bit sloppy. So V1 times T2 divided by T1 equals our final volume. We're not quite ready to add in numbers yet because we have those stupid Celsius. So what we're going to do is we're going to go ahead and add 273 to our temperature in Celsius. So our initial temperature is 600 Kelvin. And to 27 degrees Celsius, we're going to add 273, and it looks like our final volume is going to be 300 Kelvin. So my temperature is decreasing, which means I would expect my volume to decrease as well because they're directly proportional, but let's see if that's how it works out numerically. All right, so filling in, V1 is 6.8 liters times T2, which is 300 Kelvin, divided by T1, which is 600 Kelvin. I see that my kelvins cancel, leaving me with liters, which is what I would expect for a volume calculation. So we multiply across the top, or divide by the bottom, and it looks like we're going to be working with 2 sig figs. I'm looking at the initial temperatures and the initial numbers given in the problem, and the least is 2 sig figs. So the answer I report is also to 2 sig figs. So 3.4 liters is your answer. That is less than my initial volume, which is what I expect when my temperature is decreased as well. All right. Here is your sample problem that you can find in your guided practice. You can go ahead and pause the video and try that one out. Our last gas law is Gay-Lussac's, and in Gay-Lussac's we are looking at the pressure of a gas and how it's related to the temperature in Kelvin. These are directly related, which means as one goes up, the other is going to go up. As one goes down, the other is going to go down. This time we are holding volume constant. So using our little magical, I'm calling it a magic triangle. It's done. It's sold. It's marketed. Using our magic triangle, we are going to hold volume constant. So I'm going to hold my thumb over that, pretend that side's not there. And this is Gay-Lussac's equation. It's pressure divided by temperature. So let's take a look visually what this looks like. All right, so if we start with pressure of 1 atmosphere and a volume of 2 liters, and we were to increase the temperature, so temperature increases. Now notice volume is being held constant. That's important, okay? That's not changing. We increase the temperature. Notice what happens to the pressure. The pressure goes from 1 atmosphere to 2 atmospheres. It also increases. They're directly proportional to each other. So let's take a look at the combined gas law and see how these are derived. Remember, we cross out whatever's being held constant, which in this case is volume, and therefore what you're left with is looking at the relationship of pressure and temperature to each other, and as you change those variables, you should see a relationship in how the variables change. So Gay-Lussac's is initial pressure over initial temperature divided by final pressure over final temperature. All right, let's approach this as if we don't know it's a Gay-Lussac example problem so we can figure out which problem to use. All right, so the gas left in a used aerosol can has pressure of 3.6 atmospheres. That's an initial pressure. Oh, gosh darn it, at 27 degrees Celsius. I'm going to have to add 273 to that later and figure out what the heck it is. If the can is thrown into, oh my God, do not ever throw full cans or partially full cans of aerosol into a fire. That is incredibly dangerous. What is the pressure of the gas? Oh my God, at 927 degrees Celsius. Okay, so we don't know what our final pressure is, but we do know what our final temperature is. I'm going to have to add 273 degrees to that. So I'm just reminding myself there, and I'll get it in a minute. All right, so using my magic triangle, I am holding, so we have pressure and temperature. I'm holding volume constant. That means my equation is going to be P1 over T1 is equal to P2 over T2. All right, so we are solving for P2. So in order to do this, I'm going to go ahead and solve for P2. So I have to multiply this by the reciprocal, so T2 over 1. Those will cancel, and I'm going to do the same thing to the other side because you can't do one side without doing the other side. Let's rewrite this to make it look pretty again. P1 times T2 is equal to, or divided by T1 is equal to P2. Okay. So just eyeballing this, I'm noticing that the temperature goes up. I know this is a directly proportional problem, so the pressure is going to significantly increase as well. Let's go ahead and convert these guys. 27 plus 273 is 300 Kelvin for my initial temperature. And 927 plus 273, oh dear God, my T2 is 1200 degrees Kelvin. That is significantly hot. That's bad. Please don't do this at home. Okay, so let's go ahead and fill in our numbers. P1 is 3.6 atmospheres, and that is 3 times the atmospheric pressure of what you're feeling right now. The atmospheric pressure is 1, so that's 3 times that. That's amazing. And we're going to multiply this by T2, which is 1200 Kelvin. And we are going to divide it by T1, which was 300 Kelvin. Kelvins will cancel, leaving me with atmospheres, which is good because I'm looking at pressure. And now we expect the pressure to be more than 3.6 atmospheres. So multiply across, divide by the bottom, and you get 14.4 atmospheres, but that's not the right sig figs. So rounding to 2 sig figs, because that's what I have in the problem, you have a pressure of 14 atmospheres. I guarantee that can can't hold that pressure. You throw that can on the fire, it's going to blow up. It's a good life lesson. All right, so again, we're working with more aerosol cans. Go ahead and pause this so that you can try this problem. It is in your guided practice.